Okay, it looks like we have people. Does anyone object to having a midterm this weekend as per what I said on Friday and in the email? Okay,
Uh,
so hopefully I'm going to write that soon. I was doing research on the weekends and then I was writing the assignment this morning, so this is going to be a fairly random lecture. Like this isn't necessarily the best collection of topics, but whatever. We finished the course material, so let's do some stuff. So last time we were talking about this idea of the of operators. So an operator is in general a linear map from a vector
Hello.
space to itself, but we'll care about. Oh, wait, was that a comment?
Yeah, sorry, my mic wasn't on earlier, I think. I had not necessarily a super strong objection, but I was wondering if it would be necessary to be this weekend. It was a bit short notice for me in particular, but it's not a big deal if it's what's on the schedule.
Well, there wasn't a schedule, and that's my fault. But also, like next weekend would be too late, and during the week, more people will have conflicts.
Yeah, that makes sense. Okay, cool.
Okay, so if it's like send me an email if it's like a very bad conflict. This isn't supposed to be a 2-day midterm. It's supposed to be a 1-day midterm. I made it 2 days to decrease conflicts.
Oh, okay, awesome. Thank you. That's just the thing is I'll be traveling and stuff, and that's what I was wondering about.
Right. So if you're missing like a day of the exam, but you're actually going to have a day, then it's still going to be fine.
Yeah, I should be, if it takes like a day, I should be able to do it, like sparse out the time to finish it on time.
Good. Okay, good, good.
Thank
If you're
you.
worried, send me an email. Okay. And in particular, anyway, so operators, we care about operators from function spaces to function spaces. And so, for example, if P of X is some polynomial, then we have the operator P of D, which is what we saw in these constant coefficients linear homogeneous equations, well, constant coefficient linear equations in general. And then sort of A naughts times the identity, but we usually don't write that. And then what we had was this exponential shift theorem. That we very briefly discussed last time. And what the exponential shift theorem says is that if you have one of these polynomial differential operators applied to a function that is of the form u times an exponential, then that's the same as taking this exponential out front of the differential operator. So this is sort of acting as multiplication on the results of applying P of D plus A to U. And I am actually going to go and prove this. So proof. This is probably the very first proof that we're doing in this entire course. So if so observation 1 is that it suffices to prove this for P of X is equal to X to the K. And the reason is that this entire equation is linear. So if P is the sum of two things, then both sides can be broken up as the sum of two things. Sort of if we do P plus Q of D U e to the AX, and that's the same as P of D U a to the EX, sorry, e to the AX. plus q of d u e to the ax. And the same is true for the other side as well. So basically, if we can verify it for just these generating monomials, the same is true for scaling by a number, then it's we by linearity get the result for all polynomials. So then we're going to argue by induction. So case one is that n is equal, k is equal to 0. Then all that the differential operator is, well, rather, let me write this in a bit. So k is equal to 0. For the k equals 0 case, we have that p of d is just the identity operator. So we have sort of 1 applied to u e to the ax. Well, that's equal to, I guess, e to the ax with 1 with the substitution x goes to, rather, d goes to d plus a. This is using programming language notation. So we make the substitution inside of this formula. We replace all occurrences of d with d plus a. And that's nothing. Which is just both of these sides are u e to the ax. There's nothing to prove in the case for 1 because it's just the identity operator. Now assume that for p is p of x is equal to x to the k, that's the result holds. Then what we're going to do is we're going to consider p to the x to the k plus 1. Then if we consider d of x to the k plus 1 applied to u e to the ax, we can alternatively write this as d of d to the k u e to the a. And then by our hypothesis that the theorem is true for k, we get that this is d of e to the ax by d plus a to the k applied to u. Now, this is just differentiation, so we get our product rule expansion. So this is a e to the ax d plus a to the k applied to u. And then if we just differentiate that, we get e to the x d of d plus a to the k applied to u. And then grouping these terms together, here we have d, and here we have a. So that's e to the ax d plus a. D plus a to the k of u, which is e to the x d plus a to the k plus 1. So how induction works is that we show the result is true for k equals 0, and then we show that if it's true for k, it's true for k plus 1, and that proves it for all natural numbers. So therefore, it's true for all these generating monomials for any sort of exponents, and by linearity, it's true for all other cases. So I will label this as the inductive case. And that's how you prove theorems by induction. Any questions about that? So here, I'll do an example. Let's say we have something like d minus d squared minus 2d plus 3 applied to x cubed e to the negative 2x. Well, the left-hand side can be factored. How does it factor? Yeah, it does factor. So it's d minus 3d plus 1, right?
But then it would
Eh.
be d squared minus 2d plus.
Oh, sorry. Yes, I actually do want to. I made a typo. Yeah, so in order to make this happen, I need to write minus 3. So I think the original problem didn't have this, and you're right, exactly. Okay, modifying the problem, minus 3. Okay, now it factors. X cubed e to the negative 2x. Yeah, thanks. Sorry about that. Then I can pull out the e to the negative 2x at the fronts. And what happens is that d becomes d minus 2. So this is d minus 5. That looks like a 6. And then d minus 1 applied to x cubed, which is e to the negative 2x. And then we're going to actually unfactor this. I didn't have to factor it originally. I could have just substituted d minus 2 into the equation and then expanded it out. So the factoring was entirely superfluous, but it helps a bit. So d squared minus 6d plus 5, I think is the results, applied to x cubed. And okay, so what do I get here?
Six x
Mhm.
minus 18x squared
Mhm.
Plus 5x cubed.
Exactly. So for polynomials, it's easy to differentiate. Now, this would be much harder if you actually took like the second derivative of this and did chain rule. Sorry, product rule. If you did a product rule derivation of this, you get a lot of terms. And in the end, they'd recombine to this, but it's a bit easier with the exponential shift theorem. Okay, now we're going to do something pretty wild. So we're going to talk about inverse operators. So with the equation, if we want to solve, the equation P of D applied to Y is equal to some function f of x. So this would sort of be, in this case, this would be a constant coefficient linear equation, and this would be a inhomogeneous constant coefficient linear equation. Then what we're going to do is, let's just write that y is equal to 1 over P of D. applied to F. That would be an unreasonable thing to write, but what does this mean? This just means that 1 over P of D is some operator. Such that 1 over P of D of F solves the equation. So that's the meaning of this. Therefore, by just defining this to be something, an operator which gives the solution, I really haven't done anything new. I've just defined some notation to stand for something. So I'll give you an example. Let's suppose that we have something like 1 over D squared applied to 2x plus 3. Well, what this is equivalent to is to saying that for y is equal to this is equivalent to saying, okay, let's say y is this. That's equivalent to saying that d squared y is equal to 2x plus 3. Now, in general, if we have the second derivative of y, then that implies that y is equal to, we're going to integrate twice. So we're going to get a factor of 2 here, and then we're going to get a factor of 3 here. So it's going to be 1/3 x cubed plus, then when we go up to 2, we're going to get a factor of 2 x squared, and then you'd have cx plus d as your constants. Now we want like a particular operator that does something. So the solutions to the homogeneous equation are exactly the second derivative of y is equal to 0, are exactly this cx plus d. So we will pick the simplest solution. That removes any visible multiple of solutions to the homogeneous equation. Well, not exactly multiples, any additive factors that solve the homogeneous equation. So we'll say that the correct solution to take is that 1 over d squared 2x plus 3 is just going to be, well, we want to be some solution, so we're going to choose the simplest solution. And this isn't fully mathematically precise, but you'll see how it helps in solving problems. In the end, what we care about is finding one particular solution to the inhomogeneous equation, because then we just add all solutions to the homogeneous equation to get the general solution. So, okay, that's how we solve the inverse operator in the case of just having something that's 1 over d to the k. Now, let's do the next simplest case. Suppose that we want to find 1 over d plus, let's say, d minus a naught. And let's say that our particular solution is going to be a monomial. It's going to be bx to the power of k. maybe I should split this off because this is going to be a bit of an extended calculation. So in other words, I want to solve the equation y d rather y prime minus a naught y is equal to b times x to the k. And so let's just solve this equation without using inverse operators for a second. And I'm going to use the ansatz. And this can be motivated in several ways, but at the moment, I'm just not going to motivate it at all. And the ansatz is that y is going to be some polynomial of x. So let's say a to the k, x to the k, plus dot 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 plus a naught. Then, and by the way, a naught is not equal to 0. Then what's going to happen is that if we differentiate y, we're going to get k a to the k, x to the k minus 1, plus let's say k minus 1, a to the k minus 1, x to the k minus 2, all the way down to, well, a naught disappears, so we get a1. And so y minus y prime minus a naught y is going to equal minus a naught a to the k, a sub k x to the k. That's going to be the leading term and the only term with x to the k as its power. Plus k a sub k minus a naught a sub k minus 1 by x to the k minus 1. And then this is going to continue all the way down to the last term, which is going to be a1 minus a naught times a naught. And so we get the equations that if we want to see what this is should equal, it should equal b to bx to the k. So b is equal to the leading coefficients, which is k a sub k. Then all other coefficients are 0. So 0 is equal to k minus 1, a sub k minus 1, minus a naught, a sub k here. All the way down to 0 is equal to a1 minus a naught times a naught. So what this tells me is that a sub k is equal to b divided by k. Sorry, there's a mistake. That's not what the leading coefficient is. The leading coefficient is minus a naught. Yeah. Okay, so that tells me that a sub k is minus b divided by a naught. Then what this equation tells me after I rearrange it is that a sub k minus 1 is equal to k minus 1 sorry, also another mistake. This is k a to the k. Yeah. Is k a to the k divided by a naughts, which by our previous thing is going to be minus bk divided by a naughts squared. And in general, each one of these equations rearranges to a sub k minus L is equal to so it's going to be if we have so we have a k minus L, we're going to have k minus L here. And then we're going to have minus a naught a to the k minus L minus 1 is equal to 0. And so a to the k minus L minus 1 is equal to k minus L times a to the k minus L divided by a naught. And so, for example, that means that if we start off with minus b, so we're going to start off with minus b divided by a naught, then we're going to get minus k b divided by a naught. Then we're going to multiply the previous one by k minus 1. So it's going to be minus k times k minus 1. Sorry, this is squared. B divided by a naught cubed. And in general, the formula is going to be that's a to the k minus L is equal to negative b. And then I'm going to use this notation for the falling factorial. Divided by a naught to the L plus 1. Where if you have sort of k to the 0 falling factorial, then that's just equal to 1. And k to the n plus 1 falling factorial is equal to k times k minus 1 to the n falling factorial. So for example, if we have something like 6 to the third, that's equal to 6 times 5 times 4. So we take 3 terms in this descending sequence. And so what we get as a result is that y here is a particular solution from the ansatz. So this ansatz gives us a unique solution, but that's not the general solution. But it is a particular solution to the inhomogeneous equation. So notice that every single one of these coefficients has a power of b divided by a naught inside of here. So we can also write this as minus b divided by a naught times k to the L divided by A naught to the L. So y is minus b divided by A naught times, and then we can write x to the k plus k over A naught x to the k minus 1 plus k times k minus 1 divided by A naught squared x to the k minus 2, if those terms exist, all the way down to k factorial divided by A naught to the k. Just the constants term right here. So that's our particular solution to y. So from this onset, we were able to solve it, and this is what it looks like. Now, so that's the particular solution. But how about second method? So let's calculate 1 over d minus A naught times b x to the k. So I will give you a hint. I'm going to write this as 1 over A naught times 1 over 1 minus d over A naught. Now, what would be the most ridiculous thing that I could possibly do right now, which is correct?
Wait, but that doesn't, that's 1 over A not minus D.
Yeah, sorry, I want a minus here. Good. Okay, yes, I factored out the minus A so that the coefficient on the 1 became a 1. Why did I do that, though? What is this suggestive of? So what does 1 over 1 minus x equal? So the answer is it's a series. This is equal to the sum from n is equal to 0 to infinity of x to the n. So in particular, for example, if you sort of have 1 plus 1/2 plus 1/4 plus 1/8, so this geometric series, then that's equal to 1 over 1 minus 1/2, which is equal to 2, right? So this is how you sum a geometric series. So this is the Taylor expansion. At 0. Well, I guess Maclaurin expansions are Taylor expansions that are not at 0. Taylor expansions are always at 0. So what the most ridiculous thing that we could possibly do is say that this is equal to negative 1 over A naught plus 1 plus d over A naught plus d squared over A naught squared. And then the thing is that this is an infinite series, but we're applying this to a polynomial which has a certain degree. So that only the derivative up to the kth order is going to matter. So as far as calculating this is concerned, we only go up to a certain order. So it was very important that we were applying this inverse operator to something that was a polynomial, in other words. Well, what does that give us? That gives us, well, the b comes out front, so negative b over a naught. Then we just get x to the k plus, well, when we differentiate this once, we get k x to the k minus 1 over a naught. Then when we differentiate it twice, you now see where the following factorials come from. And then if we differentiate x to the k times, we get k factorial. And then we get this over a naught to the k. And if you look at this, this agrees with our previous answer, except for the fact that the terms are written in their terms are written in the same order. So instead of doing all of this math and noticing what the pattern is and arguing the pattern by induction, we could have just used the series expansion, and that would have actually gotten us to the correct answer. So in other words, this checks out. This does make sense. So suppose that p of 0 does not equal 0. So in other words, the constant coefficient of p is non-zero. Then how do we find the series expansion of 1 over p? So first off, why am I imposing this restriction? We want the series of 1 over a n x to the k plus dot dot dots plus a naughts. Well, we want this series around 0. And if a naught does not equal to 0, then this function is not defined at 0. And so we can't write out a series for it at 0. This only makes sense if a naught does not equal to 0. Because otherwise we can't write out the series at 0. Well, so how do we do this? Well, if this has a series, which it will, if a naught is not equal to 0. So suppose that that series is the sum from n is equal to 0 to infinity of b sub n x to the n, right? Then 1 is equal to the product of this polynomial. Sorry, why am I writing a sub n x to the k, a sub k? And if we think about that, then what's that equal to? Well, you can actually multiply this series by a naughts, then all of the terms get multiplied by a naughts. Or you can multiply it by a1x. And if you multiply it by a1x, then it shifts all the terms and multiplies them by a1. So what this is equal to is it's a naughts, b naughts, plus a naughts, b1x, plus a naughts b2x squared plus a naughts b3x cubed, and so on. Plus, now we're going to multiply by a1x, and this shifts all of the terms. a1 b naughts x, because there's a shift going on, because now we're multiplying by a1x, plus a1 b1x squared, plus a1 b2x cubed. Then here we're going to get a 2b naughts x squared plus a 2b1x cubed. And then here we're going to get a 3b naughts x cubed, and so on. And so this is equal to 1. And 1 is a polynomial whose series expansion is just 1 and then zeros for all of the higher polynomials. So if these two are equal, then all of their coefficients should be equal. So that tells us that 1 is equal to a naughts b naughts. And that's 0 is equal to, that's the next coefficient. And then sort of we go down these columns. And you can actually see what the pattern is pretty easily. If I write out the first two, you'll see what the pattern is. So it's a naughts b1 plus a1 b naughts. For the next one, it's a naught b2 plus a1 b1 plus a 2 b naughts. So how it works is that here the budget is 0. And so A and B have to have 0 when you sum them. Here the budget is 1. So you can allocate 1 between A and B. Here the budget is 2. And so in general, you get these convolutions. So for example, for the next one, without even looking at this, is going to be A naught B3 plus what's all the possible ways to get a sum of 3 between these two, plus A1 B2 plus A2 B1 plus A3 B naughts, right? And so, for example, you get that, and do not memorize this formula, 100% do not memorize this formula. You get, for example, that we are trying to solve for B naughts, that B naughts is equal to 1 over A naughts. Then here, what you get is that B1 is equal to negative A1 B naughts divided by A naughts, which is equal to, given what B naught is, negative A1 divided by A naught squared. Then here, for example, you get that B2 is equal to 1 over A naught, let's say minus 1 over A naughts, by A1 B1 plus A2 B naughts, which is going to give us, so when we plug these in, well, when we plug this in for B1, we're going to get A1 squared, the minus signs are going to cancel out, so A1 squared, and then A naught at the bottom, and then so divided by A naughts cubed. And then here, what we're going to get is A2 times 1 over A naught, so minus A2 over A naught squared. Anyway, so in general, the point is that you can solve these equations. You solve them one by one, right? However, that's not how we're actually going to do this. We're not going to do this general formula and then get the coefficients. You see that it gets a bit messy after a while. So instead, let's look at an example. Let's say you want to solve something like so I'll break this off. Maybe for green line this time. Let's say you want to solve something like 4y prime prime minus 3y prime plus 9y is equal to 5x squared. Then you're going to consider p of x is equal to 4x squared minus 3x plus 9. And we want to find the series expansion of 1 over 4x squared minus 3x plus 9. Well, here's actually a better way to do it. First off, A naughts is usually very annoying, and we're going to get increasing multiples of A naughts. So there's going to be like an A naught cubed. And so it's better if we factor out A naughts at the start. So let's write this as 1/9. 1 over, and then let's rearrange the coefficients. So it's 1 minus 1/3 x plus 4/9 x squared. Now, if you want to divide something by something, what do you do?
Polynomial division.
Yeah, polynomial long division. Let's do polynomial long division in order to find an infinite series. Why not? So the polynomial long division is 1 minus 1/3 x plus 4/9 x squared divided by 1, right? So how does this work? Well, 1 goes into 1 once, right? So then you're subtracting 1 minus 1/3 x plus 4/9 x squared. And so when you subtract, the result that you get is plus 1/3 x minus 4/9 x squared, right? Now, 1 goes into 1/3 times, but it's x, so it's 1/3 x. Then we get 1/3 x, then we get minus 1/9 x squared minus 4, or rather plus 4 over 27 x cubed, although we actually don't care about the x cubed term at all. Why? Because the polynomial that we're starting with is x squared, so we're going to take this up to x squared. So I'm going to leave this term here for now, but we're going to see that it actually doesn't matter. So when we subtract this, we get minus 4/9 plus 1/9, which is 3/9, which is negative 1/3. Then how many times this go into this? It goes in minus 1/3 x squared times, right? And then we get minus 1/3 x squared, and then we get whatever here. And the point is that this is 0 plus whatever, right? That looks like a 0. I want to say whatever. So we have found the first 3 terms. So it's going to be this plus whatever, right? But because we only care about finding the inverse up to second order, because we're going to be applying it to 5x squared, we stop there. So you can actually do polynomial long division, and it's great. So polynomial long division lets you do this process that we did here and solve this sequence of equations, but it lets you do it in a much more systematic way where it's just like you learned division in what, grade 2 or grade 3? I don't know, grade 2 maybe. And so you just do it. And so what do we get as a result? As a result, we get that that is equal to 1/9 times this inverse, which is 1 plus 1/3 d minus 1/3 d squared. Applied to 5x squared. And then we just do the differentiations. So here we get 5x squared. Here, when we differentiate, we're going to bring the x squared down, so it's going to be 10 thirds x. And then we're also going to get 5 times 2 here. So minus 10 thirds, and then both powers go away. And so, yeah, that looks right. And that's the answer. And that answer is correct. So that's a particular solution to the differential equation. This is a particular solution. And in this course, I've generally been writing down general solutions, but in this section, I'm just going to write down the particular solutions. Because we know how to solve the constant coefficients homogeneous equations. Okay, I think it's time for a break because I don't have time for another example. So let's resume at 7:05. Right. Okay. See you then. Okay, let's continue. Right. So the next order of business is what if A naught is equal to 0? Then what happens is that P of X is equal to, let's say it's going to be X to the M times, so X is a factor of P, times A, let's say N, X to the N plus dot 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 plus A naught. And so what happens when we do this inversion is that if we're solving for P of D of Y is equal to BX to the K, then there's two ways that we could do it. We could either say that Y is equal to 1 over D to the M, which is just going to be integration of 1 over A N X to the N plus dot 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 plus A naught applied to B X to the K, which we just discussed how to calculate. So you do them separately. So this has a series, and then this is just repeated integration. The other way that you could do it is you could swap the order. However, this way is worse. And the reason is that integration is going to raise the degree of this polynomial, so you're going to have to calculate this to higher order. So this is the way to go. And in fact, these two won't necessarily give you answers that agree, because you might get some multiples of solutions to the homogeneous equation if you do this way. But both are going to give you particular solutions. So this equality is sort of an equality in quotes. 1 second, what's going on with my earbuds? They should be fine. Okay, yeah. So to give an example, let's say we want to solve, well, this is sort of very easy. Y prime prime minus 2y prime is equal to 5. Then what we have is that this is y is 1 over d by 1 over d minus 2 of 5, which is, well, let's factor out the minus 2. Then we get 1 over 1 minus d over 2. However, we really don't care about this because 5 is a constant. And so when we do the series expansion of this to first order, it's just going to be 1. The next term is going to be minus d over 2, but we don't care about that. So this is 1 over d by minus 1/2, and then I just guess the operator 1 applied to 5, which is 1 over d of 5/2 minus 5/2, and when we integrate that, we obtain minus 5x over 2. Okay, let's do a slightly more interesting example. Let's say y to the 5th derivative minus y to the 3rd derivative is equal to 2x squared. Then what we get is the equation that y is equal to 1 over d cubed 1 over d squared minus 1. Which is 1 over d cubed. And then I guess I can write minus 1 over d cubed, taking the minus sign out front. And then we have 1 over 1 minus d squared. Well, this also looks like a geometric series, except for the fact that it's in x squared as opposed to x, or d squared instead of d. So we don't even have to do long division in this case. The series up to second order is going to be 1 plus d squared, because this looks like a geometric series. So that's going to be the third antiderivative minus the third antiderivative of 2x squared. And then if we differentiate this twice, we're going to get plus 4. And if we integrate this, what we're going to get is minus, and then what are we going to get? So 2 is going to become 3 powers added to it, so x to the 5th. And then we're going to divide by 3, 4, and 5 respectively. And 4 is going to become 4x cubed divided by, well, 1, 2, 3. And so we can rewrite this as, well, so 4, 2, 3 by 5, 15 by 2 is 30. So minus x to the 5th over 30. And then if we do this, we get 2/3 minus 2x cubed over 3, right? So by the way, let me say that what we're doing for second order equations, technically this is nothing new, because for second order equations, we have variation of parameters, right? So you could solve this equation using variation of parameters. And variation of parameters works for equations of any order. So in fact, everything that we're doing in this lecture can be done by variation of parameters, but this is an alternative method. However, I haven't told you about variation of parameters for equations of order 3 or higher, which I'm just going to do a digression, because I put one problem on the homework, which is a third order equation. So let me just talk about variation of parameters for third order equations.
By the way, is the homework up to lecture 8?
Yeah, so it's up to lecture 8, except for the fact that I put a third order inhomogeneous equation, and I want you to solve that using variation of parameters. And I'm about to tell you how to do variation of parameters for third order equations. So for third order linear ODEs. This is a digression. So let's just review. For second order equations, let's suppose that our equation was sort of like perfectly general. Let's suppose that it was y prime prime plus f of x, y prime plus g of x. So we're not assuming constant coefficients. And suppose that y1 and y2 are solutions of the homogeneous equation. Then use the ansatz. Use ansatz that y is equal to uy1 plus u1y1 plus u2y2. That was the ansatz. However, there is up to homogeneous factors 1 inhomogeneous solution to this equation. up to factors, whereas there are two parameters here. So we got to impose another condition. There are 2 degrees of freedom, and we can reduce it to 1 degree of freedom in order to be able to solve it. Then y prime is equal to u1 prime y1 plus u2 prime y2 plus u1 y1 prime plus u2 y2 prime. And let me just check which one of these we set to equal 0. So this we would have done in lecture, its second order. So in lecture 4. Okay, what about the inhomogeneous equation? Okay, then we talked about Wronskians. Okay, and then we said that, so it's lecture 5, actually. I can scroll up quicker if I just grab this on the side. So we used, then we said that the u prime term. So u prime y1 plus u prime y2 is equal to 0. Then we looked at this term. And we said we will look for solutions where this is 0. So we get an equation. We get that u1 prime. Now that I write it out, it's obvious that it's this one and not the other one. Y2 is equal to 0. So that's an equation that we have. And then let's see what we get. Then y prime prime is equal to, well, this term vanishes, so we are taking the derivative of this, and we get u1 prime y1 plus prime u2 prime y2 prime. Now we don't have any more degrees of freedom, so this equation stays. And then we get plus u1 y1 prime prime plus u2 y2 prime prime. And then if we take y prime prime plus f y prime plus g of y, what happens is this term stays. And then we're going to take this term, which has u1 and u2, this term, which has u1 and u2, and this term, which has u1 and u2. And when we combine, factor out the u1s and the u2s, we get 0 plus 0. Because y1 and y2 are solutions to the homogeneous equation. So we get a second equation, which is that this equation is equal to our inhomogeneous part, h. So our second equation is that u1 prime y1 prime plus u2 prime y2 prime is equal to h. And so then we get a 2x2 system of linear equations for what u1 prime and u2 prime are, right? And then we can solve for this. So for third order equations, which are y prime 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 plus, let's say, f of y prime prime. This is just a function of x plus g of y prime plus h of y. And then what's the next letter? F, G, H, I. Well, I is a bad letter. J is a bad letter. K is the next reasonable. K also looks like an index. HIJKL also looks like an index M. E is also a bad letter. Whatever. K, sure. It's going to be K. So what we're going to do is suppose that y1, y2, and y3 solve the homogeneous equation. Then we're going to use the ansatz that y is equal to u1, y1 plus u2, y2 plus u3, y3. And when we differentiate, we're going to get that this is u1, y1 prime plus u2, y2 prime plus u3, y3 prime. And then this term we're going to set to 0 because we have 2 degrees of freedom. And then we're going to get plus u1. One second. We want to set the term with the primes equal to 0. Right? No, I'm wrong. This is a good term. Plus u1 prime y1 plus u2 prime y2 plus u3 prime y3. This term we set to 0. Then when we take y prime prime, this term is 0, so we're going to ignore it. And then we're going to get u1 y1 prime prime plus u2 y2 prime prime plus u3 y3 prime prime. And then we're going to get plus u1 prime y1 prime plus u2 prime y2 prime plus u3 prime y3 prime. And then we have one more degree of freedom at our disposal. So we're going to set this equal to 0. And then the same thing is going to happen as before. So when we calculate y triple prime, we don't get any equations. However, when we rearrange it, we're going to get the last equation, which is going to say that's only, so the last equation, so here are our equations. Our equations are that u1 prime y1 plus u2 prime y2 plus u3 prime y3 is equal to 0. Then we get u1 prime plus y1 prime prime plus u2 prime y2 prime, sorry, single prime, plus u3 prime y3 prime is equal to 0. And then the last equation, as before, is going to be that u1 prime y1 prime prime plus u2 prime y2 prime prime plus u3 prime y3 prime prime is equal to the inhomogeneous part, so k of x. And this is going to happen for the same reason as before. So we're going to calculate the third derivative. It's going to give us both terms again. The one term is going to be this, and then the other terms are going to rearrange to 0 plus 0 plus 0, and that should equal k. So what happens is now you have a 3x3 linear system. For u sub I prime. And so you solve it because we know how to solve 3x3 linear systems. And then integrates to get u. Okay, so that was a digression for the sake of exactly one homework problem and also midterm and final problems. But now you know how to solve third order systems. And by the way, you can imagine that this actually extends to all higher order systems. If we are doing a fourth order system, then we're going to get another series of equations. So for fourth order systems, I'll just write it out. You're going to get the equations. And then you can sort of predict what it's going to be. It's going to be u1 prime. Let me write them in green. And then I'm just going to copy this equation and modify it. So in the second order, then we're going to get primes here. Then we're going to get double primes here. And then for the last equation, we're going to get triple primes here. And what we get here is actually sort of, I'm just going to write it as F, the inhomogeneous part. So this extends to sort of any order of differential equations, and then you solve the system. Okay, so that's okay. Technically, now you know how to solve any linear differential equation in which you can solve the homogeneous part, and you know how to solve the homogeneous part in any higher order equation, because you just use the ansatz e to the tx, and then if there are repeated roots, you just add an appropriate power of x. Okay, let's see where we were when we last stopped. So we talked about how to solve equations like this. Well, okay, here's how you'd solve them using variation of parameters. You'd have a 5x5 system in that case, and that just sounds terrible. So you'd never actually use variation of parameters. And this way is distinctly easier for like fifth order linear systems, which we're able to do. However, we're only able to do it at the moment if the inhomogeneous part is a polynomial, right? Because the method doesn't work because you can't just stop taking terms here if it's something other than a polynomial. So that's a bit sad. But I'm now going to extend it from the class of polynomials to the class of polynomials multiplied by exponentials, because we get an exponential shift theorem for inverse operators. The fact that I chose to cover this material in class is sort of random, because we finished the course material and I had lots of choices as to what I'd actually cover. And I started doing this a while ago. So this is sort of like, I guess, I mean, it's part of the course material. It's going to be examined, but it's, as far as we're concerned from the material, a curious and weird extra topic. We're not technically learning how to solve any new equations, but it does give a shortcut for like very specific class of inhomogeneous equations of the form x to the k e to the ax. We can solve homogeneous equations of this form. It also extends to cosine and sine if you sort of do real and imaginary part arguments. Anyway, so what does the exponential shift theorem say? Well, if we sort of have 1 over p of d, this inverse operator, applied to some function u e to the ax, then it says that that's equal to e to the ax 1 over p of d plus a applied to u. And so here's the proof. So first off, okay, let's go here. Because it's getting up, it's too hot to cuddle a shark this entire time. So e to the ax u is also equal to e to the ax. And then we can say p of d plus a to the 1 over p of d plus a applied to u. And this is by the definition of an inverse operator. If we apply the inverse and then we apply the differential operator, it should give this a solution. So, but then the But then the exponential shift theorem applies to this outer one because we already know how that works. So that's equal to P of D applied to e to the ax 1 over P of D plus A applied to U. But then we can also write that e to the ax times U is also equal to, I'm going to do P of D, P of 1 over D. 1 over P of D, e to the ax U. And so as a consequence of these two equations, we get that 0 is equal to P of D. And then by linearity, we get e to the ax 1 over P of D plus A of U minus 1 over P of D e to the ax U. And so if we're solving this equation, then sort of, okay, so because of some very weird conventions in how we remove solutions to the homogeneous equation, we can, I guess, it also makes sense that 1 over P of D 0 is equal to this expression. I keep replacing my x's with k's. So this is going to be very sketchy. Why is this true? Why can we cancel it in that direction? Does that make sense? Well, if you sort of write out all the conventions clearly, it does make sense. And this expression right here, a particular solution to 0 equation because it's linear is 0. So that tells us that 1 over P of D, rearranging this equation, to the ax U is equal to e to the ax 1 over P of D plus A. So that was a bit of a sketchy proof, I will admit. But let's see what this implies. So let's do an example. Let's do something like how much more material? Oh, I see I have more material. That's good. Let's do something like y prime prime minus 2y prime minus 3y is equal to x squared e to the 2x. So what happens is we look at 1 over d squared minus 2d minus 3, which actually is something that factors. Yeah, this is the thing that factors. That's what we saw last time, incidentally. I did not factor it in the solution to this equation. But that sort of makes the calculation a bit easier. So by the exponential shift theorem for inverse operators, this is e to the 2x. And you know what? I'll just factor it for simplicity. Which is e to the 2x by 1 over, then we get d plus 2 minus 3, so d minus 1. And then here we get d plus 2, so d plus 3. And then let's do this polynomial entirely. There is another trick that we could do, but I'll save that for the next section. D squared then we get, so plus 2d minus 3 is what happens. Yeah, and that's right. That agrees with what I have in my notes. And now we're going to use this teleportation bubble and write out a calculation. It's the second order. So let's actually factor out, you know what, before I do the teleportation bubble. When we do these polynomial long divisions, it's much easier if the leading coefficient is 1. So let's factor out a negative e to the 2x divided by 3 of 1 over 1 minus 2/3 d minus 1/3 d squared. Because otherwise we're just going to get large powers of 3 there. Okay, now using the teleportation bubble to have an unbroken chain of equalities and writing out this polynomial long division. So 1. Plus 2/3 x. And then I'm not going to care about, so this is going to become minus 4/9 x squared, and then there are going to be higher order terms. Then so I have 3/9, and then I'm adding 4/9, which is going to give me 7/9. So then I'm going to get 7/9 x squared. And that does the expansion to second order. We don't care about third order coefficients. So what that gives me is negative e to the 2x over 3. And then we have 1 plus 2/3 d plus 7/9 d squared applied to x squared. And that gives me, so x squared, then one derivative plus 4/3 x, then plus 14/9. Yeah. And that is a solution to the equation. So now we know how to solve equations that aren't just polynomials, but that are polynomials multiplied by exponentials. And this is much shorter. This is easier than variation of parameters. Now I'm going to mention something that's I actually don't think is that useful in the long run. But anyway, because we could do polynomial long division and it works, but instead of doing polynomial long division, you could do something else. Let's say you have something like y triple prime minus 5y double prime plus 8y prime minus 4y is equal to 2e to the 4x times x. Then, if you're considering 1 over d cubed minus 5 d squared plus 8 d minus 4, well, what you can notice is that if I plug in 1 into this equation, then I get 8 plus 1 minus 5 minus 4. So 1 is a solution to the equation. And so if you factor it fully, you get d minus 1 by d minus 2 squared. But then we can do partial fractions. That's the idea. And that'll help us find the series. So if we have 1 over x minus 1 by x minus 2 squared, we can write this as being a over x minus 1 plus b times x minus 2 plus c x minus 2 squared. And then if we sort of expand what that is, that's a by x minus 2 squared. So I can write that as x squared minus 2 plus 4x. Oh, wait, it's minus 2, so it's minus 4x plus 4. Then b we multiply by x minus 1 and x minus 2, and the product is going to be x squared minus 3x plus 3. And then we're going to get c, and we're multiplying this is by x minus 1. And if we rearrange this, what we get is a plus b x squared plus minus 4a minus 3b plus c x, and then plus 4a plus 2b minus c. Now, so then we have a system of linear equations, except in this class, we know how to solve systems of linear equations. And we can write this as the following thing. So a plus b 1 1 0 minus 4 minus 3 1. Let's actually apply our idea for how we solve systems of linear equations. And then this is the x squared, so it's 0 0 1. Okay, so let's reduce this. We get 1 1 0. Then we're going to add 4 here, so it's going to be 0 1 1. Then we're going to subtract 4 here, so it's going to be 0 minus 2 minus 1. So in your original calculus class, you did not do partial fractions by using row reduction. But now we know row reduction, so instead of writing out a messy system of equations, it's actually easier to do this. Okay, we'd like to get rid of this coefficient. Actually, what would I like to do? I would like to get rid of this coefficient first. Okay, let's get rid of this coefficients. So I'm going to get 1. Then I'm going to subtract 1 here. 0 minus 1. 0 1 1. And I also want to get rid of this coefficient. So I'm going to do 0 0. Then I'm adding 2 here. Then I'm adding 2 here. So I get 1. And then I'd like to get rid of those. So I get 1 0 0 0 1 0 0 0 1. And then here I have to add 1. So here I add 1, and here I have to subtract 1. So here I subtract 1. That implies that A is equal to 1, B is equal to -1, and C is equal to 1. So our equation then becomes well, actually, let's not put a star here. Let's just copy this over because I didn't put what the thing was. This is sort of separate. So this applied to 2e to the 4xx. is the same as, oh, it says my battery is low. Hopefully, how low is it? 20%. Okay, no, it's going to last the rest of this lecture. So then we get 1 over d minus 1. Minus 1 over d minus 2 plus 1 over d minus 2 squared applied to 2e to the 4x x, which is equal to, by the exponential shift theorem, e to the 4x. Then what we're going to do is we're going to replace d by d plus 4. So 1 over d minus 3 minus 1 over so plus 4. So it's going to be plus 2. This is d plus 3. And then plus 1 over d plus 2 squared by 2 applied to 2x. And we can sort of factor this. So we're going to factor 1/3 out. And then I'm going to write it in sort of the standard form. This is just suggestive. Then here, what we're going to get is there's 1/4 really. And then I can write out what the equation is, and here we'll have to do some polynomial long division. So it's going to be 1 plus 1/2 d plus 1/4 d squared. No, if I do this, no, I get 2d. So it's actually going to be, this has a 4 and that has a 4. So it's d, wait, is it? No, we get 4 here and we also get 4 in the middle. Yeah, no, it's d. I made a mistake in my notes. And so this is going to be e to the 4x 1/3 1 minus d minus 1/2 1 minus sorry, this is d over 3. This is d over 2. Okay, then plus 1/4, and we'd like to know what the expansion to this is to first order. Well, to first order, the d squared term is sort of not going to matter. So it's, you can ignore this term and expand this to first order, and then you're going to get 1 minus d. So when you're doing the polynomial long division, this term isn't going to affect the outcome at all if we're doing it to first order. And then we know how to solve that. I think that, yeah, I'm not going to expand it by that much because I'm going to end today's lecture a bit early. So we're not going to have another break. We're going to end instead. Then I get e to the 4x. Then I get, so I guess if I combine the x, I'm going to get 2/3 minus 1 plus 1/4. And then if I look at the derivative, I'm going to get 1/3. So minus 1/9. Then here I'm going to get It's a 2x. Sorry, 2/9. Then here we're going to get, so this is minus, this is plus, 1/2, and then plus minus 1/2. And so that's going to give me e to the 4x. This is just minus 2/9. And then if I do this math, I'm going to get, so the common denominator is 12. So it's going to be 4 minus 12 plus 3. And that's 7 minus 12 is minus 5. I got a different answer in my notes. Okay, I got a different answer in my notes. So there is an arithmetic mistake somewhere in one of the two things. Actually, no, that's not necessarily true.
Because there was that mistake before.
Sorry. Yeah, that mistake before probably changed it. Yeah, okay, that's a good point. Yeah. Anyway, let's try this. So I think this is right. So that's now, okay. Why did I have to do partial fractions? Perhaps I could have just done polynomial log division at the original point, and that might have actually been easier. But I wanted to show you that you can also do partial fractions. That's also a valid strategy. Do I want to say anything else today? I guess I'll do a preview of what we're doing next time. So I'll just define what a Laplace transform is. So if this is the heading of Laplace transforms. So if f of x is defined for x is greater than or equal to 0, then we define L of f to be the function. L of f applied to some argument s is equal to the integral from 0 to infinity of e to the minus sx. So that's the dependence on s inside of this formula, f of x dx. And so the thing that we note is that this is clearly linear in f. So if we write f plus g, then at every single point, we can just break this up into two integrals. So this is an operator. So this is going to be an interesting operator. It's not going to be the polynomial operator, but it's this Laplace transform operator. Let's do one example. What's the Laplace transform of the function 1? So this is going to be some function of s, and it's going to be the integral from 0 to infinity of e to the minus sx times 1 dx. And we can write that as minus 1 over s e to the minus sx evaluated between 0 and infinity. Now, this only makes sense when s is positive. So for s is greater than or equal to 0. So the domain of this function is only going to be values greater than or equal to 0 as well. Then when we plug in an infinity, we have minus s infinity, so that's going to be 0, and then we subtract the other endpoint, 0. So we have 1 over s. So the Laplace transform of the constant function is the function 1 over s. And that is all that I have for today. So next time we're going to discuss Laplace transforms, and then there are several other things. The course description for this course, the start of the summer semester had Laplace transforms as part of the material, but I think it got modified in the first week to take Laplace transforms out. So this was like done standardly in previous renditions of this course, but not in the last one that you can find. Hopefully the operator section was interesting. And I might do a bit more about solving things using series. Okay, so if you have any questions about the midterm, send me an email.
I don't have a question about the midterm, but is there like an itemized syllabus anywhere of all the stuff we covered?
Sure, I can send that out. It's
Okay.
going to be literally every single technique that we've covered.
Yeah. Thank you.
And the
Okay.
final is like, we could look at the notes, right?
Yeah, so the final is going to be an oral exam. I'm going to give you all of the problems in advance. So you should actually look at the notes in advance. Because the problem is that you're supposed to impress me and you have like 20 minutes to do so. So the problem is if you start looking at your notes for a very long time, then you're not doing well on an oral final. But you have you have your notes with your solutions, and then you can just quickly consult a solution and see what happens. But if you're consulting sort of the lecture notes and trying to find something, that's very bad, right? Does that make sense?
Yeah, but for the midterm, it's open notes.
Oh, for the midterm, it's an open book exam. So for the midterm, you should, okay, so the rules are that you're not allowed to look anything up online. But you're allowed to use my notes. But don't look things up online. I'll make that clear. In an email. So like the midterm is going to be like the assignments. Maybe with harder problems if I have more time to write it. So the less time that I have to write it, the easier the problems are going to be. That's how it works. So hopefully if I start working on it tomorrow, then I can come up with better problems than there were on the assignments, because the assignments were sort of rushed and therefore I put easier problems on them. But maybe I can come up with some clever problems. I had like, when I taught Calculus B last summer, I had really good books and I had really good integration problems. But there aren't actually many good books on differential equations, which is a bit sad. And then I put some 3x3 systems. If you look up on the internet, 3x3 inhomogeneous linear systems ODEs, you literally get one result. I had to look through a series of random books, and exactly one of the 4 books that I looked at had 3 examples of inhomogeneous 3x3 linear systems. People decided that they were only going to test 2x2 systems for inhomogeneous linear ODE systems. And somehow, because this is so standardized, you actually can't find problems. And it's sort of hard to make up a problem because the numbers have to be just right. If you write something down, the integrals aren't going to be solvable. So I could have designed my own problems, but that takes a very long time and like a lot more thought that it does take to solve them. So I would prefer to actually pull them from somewhere. But then there aren't sources. So if I have a lot of time for the midterm, then I'm going to come up with some of my own problems, and they're going to have good integrations, but I don't know if that will happen. But otherwise, it's like 2 days to do an assignment using the notes. So it's not bad. I don't feel like giving anti-cheating speech right now. At some point, I am going to give an anti-cheating speech on the midterm, saying that if you look answers up online and you don't know what you're doing, it's going to be obvious to me, and then you're going to get screwed. So don't cheat. Okay, the long form of the speech later. Anyway, okay, have a good night. See you on Wednesday.